Welcome to Bite-Sized Data Science. In the last few videos, we've been exploring and preparing data from the Chicago accident dataset. This time, we'll be doing some modeling on the data. We could look at this modeling as part of the data understanding. At the end, the type of models developed here could even end up being deployed. I am using the IBM Watson Studio environment to run my notebook. If you are interested, you can find a link in the description on how to create a free account on that platform. Links to the notebook I'm using here are also available in the description. I am using the data that was prepared in video 61. The data itself is stored in a DB2 database. The data includes multiple categorical attributes. We first create a few lists to keep track of those attributes. Note that I should have used the same naming convention for the categorical columns names when I processed the second list. This would have saved me some coding. I also identified the columns I don't want to use in my modeling. The next step is to create the SQL statement that will retrieve the data we want. The preparation of the Chicago accident table created multiple reference tables, and we need to access these tables to retrieve the attributes we want. We start by retrieving information on the Chicago accidents table attributes. This is used to create the SQL statement that is then used to retrieve the needed data. We use Python to create the statement. In brief, the code handles the dereferencing of attributes that point to the other tables and uses the grouping column from each reference table. This was part of the decisions made in video 61. Please review that video for more details. The other main thing in this statement creation is that I don't retrieve all the data, but instead I sample around 2% of the data, which amounts to 3,987 records. This is useful when developing the modeling code since it reduces the time needed to create a model. Once we are satisfied with what we're doing, we can recreate the model with all or a large percentage of the data. In this first part of our modeling, we're using hierarchical clustering. Instead of predefining the number of clusters we want, like when using k-means, this algorithm builds clusters from the bottom up. Then we can decide on a level of clustering based on the created hierarchy. Before we can create our model, we have to handle the remaining character fields. Once that's done, we normalize our data. We're using the agglomerative clustering algorithm from the SciPy library. We also use the Gover library to better handle distance calculation for categorical attributes. We have categorical values converted to numbers. In that case, the distance between these values are irrelevant. What matters is only if they are the same or not. The Gover algorithm helps us to do that. I am using a few functions that were graciously provided by my friend Robert Ullman. The next few cells simply use these functions to do the clustering. We then display the hierarchy through a dendrogram to get an idea where we want to cut it off for our final clustering. Once we select the appropriate cutoff point, we can get our clusters. This is a first try at clustering our records. We should not stop here. We can continue to tune our attribute selection and cutoff point to better understand our data and search for insights. We can take the result and display it on a map using different colors for each cluster. Note that the location of the accident, longitude and latitude, were not used in the model. This way, we can get an idea if there is potential clustering possible independently of the location. We are only using 2% of our data in this analysis. This result could be quite different if we were using it all. Also, when it comes to displaying the accident on a map, there is just so many points that should be used. In our case, our 3987 points are probably pushing the limit. If we were to use the entire dataset, we could do the sampling for the display to still get a visual representation of the result. We could also display the accidents in a Matplotlib visualization like we did in videos 17, 18, and 32. The second modeling section shows another type of clustering, dbScan or density-based spatial clustering. Identifying accident cluster locations could be useful information for insurance companies when they want to set rates for car insurance, for example. In video 17, 18, and 32, we use k-means to find the center of clusters of accidents. With k-means, we arbitrarily selected a number of clusters. dbScan will determine the number of clusters based on the parameters provided. It also eliminates points that are not considered as part of the cluster, eliminating noise points. In our example here, we are randomly selecting 20% of our dataset. The most important parameter is EPS, which defines a maximum distance between 2 points to be considered neighbors. In this example, it is set at 0.001, which represents a geodetic distance. This translates to around 364 feet. Take a look at video 45 to better understand geodetic calculations. The second parameter, min samples, represents a minimum number of points that should be part of a neighborhood to be considered a cluster. We can spend a lot of time tuning these parameters to find a clustering that makes the most sense to us. The end result of this modeling is that points may be removed from the model as noise. In fact, we can see that many points were dropped. Here, we see a Matplotlib figure that shows the points color-coded for their cluster. Let's see the cluster centers on a map. Having points on a map does not give us information on the cluster size. We can use GeoPandas with the Shapely library under the cover to dissolve all the points that belong to a cluster into a polygon using the convex hull method. We see the result displayed on the map. We can zoom in different areas and see more details on the clusters. Another advantage of using the polygons is that less objects are displayed on the map, which would be useful when using a large dataset for modeling. There is a lot of modeling work that can be done while exploring the data. Some of those models could even end up being deployed. This type of work can unlock insights from our data. See you next time on Bite-Sized Data Science, and don't forget to subscribe.